On le voit pas à l'écran, je crois.
Oh, okay.
Si toi, ça te dérange pas, mais...
And I can move the black bar, or the back anymore, but to the side or
just go ahead.
I don't know how to do it. Wait. Where's the cursor? I don't
see
know.
the cursor. I think it's okay. We can just move on.
Okay, all right.
Ah, c'est bon. Tu veux que je le coupe? Non, je le sais où.
Okay, fortunately, you don't need Zoom skills to do Shamrock, so. All right. Okay. So, well, hello everyone, and thank you for all the amazing talks we heard so far. We've been learning a lot. I'm Yona Lapeyre. I'm a PhD student at CRA Lyon with Guillaume Leb. And today I'll be presenting my PhD subject on exascale simulations of disks with Shamrock. Yeah. So let's begin. So as you probably know, we usually do a lot of theory and a lot of simulations in flat disks. But in the universe, the disks have no reason really to be flat. You can find disks that are warped. And so, and you can find that around a variety of objects. So around for galactic disks, but also around young stellar objects. And also you can have some very impressive structures such as jets, again, around young stellar objects, but also, and famously so, from supermassive black holes. So these not flat disks are exotic structures, but they're not so uncommon. So for the rest of my talk, I'm mostly focused on these. So in the case where you have a black hole and a supermassive black hole in the center of your disk, right? So what causes a disk around a black hole to be warped? Well, imagine that here you have a pure black hole. So your black hole is rotating and it's dragging space-time with it. So you have matter that is turning and unfolding. Thanks to the work of Lenz and Turing that wrote a very complicated metric in almost more than 100 years ago, we know that there is a force that is applied to your disk. And as Megan mentioned on the first day, you can model it in a much more simpler way by a post-Newtonian approximation. And it's just adding this force to your equation of motion. So as you can see, this force depends on R1 over R3 and 1 over R5, which means that it will be much stronger in the inner part of your disk rather than in the outer part of your disk. So after some time, what you expect is that, well, the outer part of the disk is not so affected by these frame driving or Lenz Turing effects, but the inner part will be strongly put back in that direction by the spinning of your black hole. So what happens between these two regions? We have a smooth transition. Does the disk break? And if it breaks, under what conditions? That's the so-called Barton-Peterson effect. So 10 years ago now, Rebecca and Daniel did some simulations using Phantom. And what they observed is that when they increased the resolution, they observed different results. So here there is a smooth transition, and here the disk is breaking. So the simulations are not converged. They managed still to have very interesting results, but there are some questions that are left unanswered or partially answered, like when exactly does the disk break, on what timescales, at what radius, can we extract some observational signature for that? Also, what's the exact influence on the accretion rate? And can we, what's the influence of very small scale instabilities, if we can reach them, on the warp of the disk? So there is only one solution for that, and it's resolution. All right, moving on to jets. As you maybe know, in disk around supermassive black holes, there are mainly two phenomena that can explain the launching of jets. So there is the Blanchard and Payne mechanism. So it's when you have a disk. So as again, your disk is rotating and matter is unfolding, and your magnetic field lines are frozen in your disk, so they're getting twisted, meaning that matter that is in your disk can follow the magnetic field line and get expelled here, creating a jet. There is also, so for the Blandford-Payne mechanism, you need a disk, and you can already say stuff with only ideal MHD. For the Blandford-Snelljak mechanism, it's a mechanism that does not require a disk, but in order to say something about it, you actually need to solve the general relativity equations. All right. Again, there have been works done on the launching of jets in disks around black holes, for instance, with the Pluto code. So this is a simulation without general relativity, just using post-Newtonian corrections. This is a simulation using general relativity. But still, there are some unanswered questions, namely, under what circumstances do you have a jet and your jet is stable? What causes your jet to be collimated? And also, what's the influence of turbulence at small scales on the emergence of your jet? Once again, only one solution, resolution. All right, so you already know what I'm about to say. Tim already presented that. So we have a new code that allows us to harness the power of modern supercomputers. It's the Shamrock code. So if we take, for example, the strongest and the most powerful supercomputer in the world, it's El Capitan, it's in the US, and you can reach 2.7 exafloating operations per second. Amazing. Unfortunately, as we mentioned, it's owned by the Department of Energy, and it's used to, among other things, run simulations of nuclear bombs, so we can't really access that cluster. But fortunately, we can access other clusters. So the Shamrock code is publicly available on GitHub. Paper was out recently, and it's the third time now that you see this, this plot, but we scale quite well. So we scale in particles per second and number of GPUs. And you see that the more you feed your GPU, the closer you are to the ideal case, which is linear scaling. All right. Now we have a code that is very fast. That's great, but we need physics to do simulations. So what ingredients do we need to simulate a disk? Well, you first need a setup. So we have the same setup as in Phantom, meaning a Monte Carlo generator. And we have what in the code we call modifiers. So essentially, modifiers are add-ons that you add to your setup to get the correct geometry and the geometry that you want. You also need an equation of state. We have several ones that we have implemented: adiabatic, isothermal, locally isothermal, another locally isothermal one. You need viscosity prescription. We have constant viscosity, Moanaga 97, the Cullen and Delem switch, this viscosity from Bodato price 20 and 10. And of course, external forces. And in our case, for the first simulation I'm interested in, the Boydin-Peterson simulation, we may need the lens steering force. All right, we've implemented all of that, but of course, we need some testing. So Rebecca, you asked about testing. We have a lot of hydro tests, but now we need tests on our disk setups to be able to trust it. All right, so in their article, Daniel and Rebecca performed two main tests on their disk setup. One is the wave-like regime term test. So as you may know, when you have a thin disk, you have two cases. One case is when your alpha Shakura-Shaniyar viscosity is smaller than your aspect ratio. It's the so-called wave-like regime. And when you have a warp in your disk, you expect it to propagate at half the sound speed. So it's not really easy to see here because we only put a very small warp to stay in the linear regime. But what we see actually when we measure the warp is that indeed we have, so this is the tilt angle in radius and in radians, and this is the radius, and we indeed see a splitting of the warp wave that's propagating at half the sound speed. Another test is testing the external force that you're putting in your disk, so the lens steering precision. Here in this test, you essentially, what I did is that I deactivated the particle interaction to just have length steering precession. And you see that the disk is breaking into annulus that are precessing independently. So actually what you measure is the time scale necessary for at each annulus for your disk to precess all the way back. All right. And actually we see what we want to see, meaning that we have the correct dependence, and we find again the fact that the denominators are cubed and r to the fifth. All right. Oh, I'm speaking quite fast. So there are also some other tests that you can run, namely the diffusive regime term. So I talked about the wave-like regime when your alpha Cherenkov is smaller than your aspect ratio, but there is another case which is greater. And in that case, you expect the warp in your disk to diffuse. So this is the equation of evolution of the angular momentum. What is important here is that you have two coefficients, mu1 and mu2. And in 2010 article, Daniel and Giuseppe proposed a method for measuring actually this coefficient compared to the alpha Cherenkov coefficient. And I'm in the process of doing that. So yeah. Now, what everyone is expecting, a big simulation of a disk, right? So that's a simulation that is currently running. So hopefully by the end of the week, we can have even better results. So it's a 100 million particle disk where I turned on the length steering effect. So we see that it's slowly turning, like slowly tilting. Yeah. So unfortunately, the scratch of the machine that I ran the simulation on was quite bad, had quite a bad bandwidth. So it's dumping that's taking a lot of time, not really the simulation. And essentially, this morning, that's where it will start to receive the beginning of the tilt, but it's not right there yet. So yeah, hopefully by Friday I can show you something different. All right. Now for the jet part, as I mentioned, we need some MHD, and we can start by ideal MHD. Well, essentially, the solver we have for ideal MHD, all right, is the same as in Phantom, meaning that, so what is difficult with MHD is enforcing that you don't have magnetic monopoles. And the method we've implemented so far is the same as in Phantom, the constrained parabolic Lagrange scheme, which means that you have your regular induction equation and you add this term, and this psi phi is essentially a cleaning field. And what it will do is that it will at each time step, it will propagate your errors outside and then diffuse them. So again, before it's flagged as production ready and able to do real science, we need to run some tests, and that's what I'm doing at the moment, namely sublinear and nonlinear tests, and especially the shock tube test, so below you shock tube and the blast wave test. That will be extremely interesting. So right now, if you don't know Shamrock, you can turn on MHD, but just know that we are still in the process of performing the tests. All right, that's a lot of talking about science. So now some ads about Shamrock. So why should you use Shamrock? We already saw yesterday that we have a very friendly interface. It's just Python. So I want to do a disk, I make a disk. I want to write a disk, I just warp a disk. I want an isothermal equation update, I just say so. Very easy. Also, we have very nice visualization tool. I'm sorry I didn't find a logo for Saracen, so just put the flower. But you can, of course, use Flash. You can also use Saracen and all the tools that it provides, like this, for instance. And as Tim mentioned, we have some native tools that help you do on-the-fly visualization. That's especially useful when you have gigantic simulations. Like, to give you a quick idea, the 100 million particle simulation, one dump is 8 gigabytes. So a bit big. And finally, last but not least, a very friendly team of developers that has a heart writing documentation. I mean, we're trying, so we have a nice website. We have also, very importantly, a feature page where you can find all the physics you can do in Shamrock, actually. And every time, so there is the name of the feature, for instance, this or that equation of state. The status, if it's green, yeah, you can use it. It has been tested, it's perfect. If it's yellow, it's still in the process of testing. If it's red, just get in touch and we'll talk about it, but we've not finished implementing it. You have the name of the person, so you can directly contact them. And if there is a paper on the subject, there is a paper that is cited if you want to see the method. All right. And yeah, and that's us. So Tim, me, and Leo, who couldn't attend, unfortunately, and mainly interested in IMR. And that's it for me. So Shamrock is almost production ready for the disk setup. MHD is on the way and is already being used for physics. So we'll be very happy to help you set up your disk simulation of your favorite disk. And thank you very much.
Thank you. Any questions? You're not expecting me to ask again, right? Any questions? Right.
Thank you very much. How do you make sure that all the development that's about to happen with Phantom, Shamrock will eventually include it? I mean, how do you manage the development of two codes which evolve separately?
So we're not, the aim of Shamrock is not to be a competition with Phantom at all. And actually, we're more in the optic of making sure that for the user, you can actually take some physics from Phantom, import it in Shamrock, and evolve what you're interested in. Of course, Phantom has years of development, and it's quite a new code. So we're slowly adding stuff, and we're very encouraging you. Of course, if you want to add things, do a pull request or ask for something. Clearly, the code is not as mature on the physics as in Phantom, but we're trying, and we have a roadmap of what's most important right now. For instance, self-gravity. And we're slowly building on that. Dust also.
I think it's not too hard to import something which works on Phantom. It shouldn't be extremely hard to.
Like we're working on compatibility with other codes that do stuff that we can't do. Like for instance with MC Post, I think a team is working on that. And for the things that we actually need to evolve simulation in Shamrock, we're working on it. And if there is something that you want that is not in Shamrock, don't hesitate to get in touch. If it's an equation of state or something like that, very easy. New setup, very easy. If you want non-ideal MHD, maybe less easy, but we can talk about that.
Any other questions? Any questions? Also, go again. No questions. So it's all perfect. Perfect code. We have 3 minutes left. So actually, I want to ask about, do you consider applications to things other than disk as well? Because actually, we're talking about resolution. It's the large scale people who are having the most trouble with resolution problems. So would you also consider selling it to other research groups as well, and especially maybe the Galaxy people or even the cosmology people?
Yes, 100%. Well, my PhD is mostly on disk, but we want the code to be used, and we are happy to add stuff to the code that helps people do different science with it.
Okay. No questions?
Yeah.
Okay.
Very good talk. I really appreciate the Saracen logo as well. So I know that for these larger particle counts, the dump sizes end up being, unimaginably large, which ends up breaking, Splash and Saracen in the process. Do you plan on having a kind of like a post-analysis, routines as well for Shamrock, just so you can do a lot of like. I'm just thinking of doing analysis after your simulation.
Yeah.
What kind of routines you have planned for that, or those simulations that are too large to use a lot of the existing tools.
Yeah. All right. Thanks for the question. Actually, for simulation up to 100 million particles, Splash and Saracen work fine. I mean, Splash is quite slow. The movie that I showed, it just took a night to do the processing in Splash, but it can work. And if you want, so you've done a simulation on a cluster, you have a very big simulation and you want to open it again, the best thing to do is actually to reopen, like to import Shamrock in the script and to use again the cluster. And as Tim mentioned, we have routines like the rendering thing that uses ray tracing on the GPU, which is extremely fast. So you can use time that you have on your GPU cluster to open your simulations again. And actually, that's something you have to think about.